Good morning, dear students. Welcome back to physics class. In today's class, I would like to discuss on Newton's law of cooling and some numerical related to this chapter. Today's first topic is Newton's law of cooling. Even though this topic has avoided from the latest syllabus, I teach you for your experimental knowledge. It was Newton who had studied firstly the relationship between the heat lost by a body in a given enclosure and its temperature in a systematic manner. Newton's law of cooling describes the rate at which an exposed body changes temperature through radiation, which is approximately proportional to the difference between the object's temperature and its surrounding, provided the temperature difference is small. What is Newton's law of cooling? According to Newton's law of cooling, the rate of loss of heat energy from a body is directly proportional to the difference in temperature of the body and its surrounding. Let us do one activity to understand how does rate of cooling of hot water depend on the temperature difference of the hot water with respect to surrounding. Take some water. It is about 300 milliliter in a calorimeter and cover it with a 2-hole lid. Fix a stirrer through one hole and fix a thermometer through another hole in the lid, and make sure that the bulb of the thermometer is immersed in the water, not the reading of the thermometer. You have to consider the temperature of the water is same as that of surrounding. Let T1 be the temperature of the surrounding. Heat the water kept in the calorimeter till it reaches a temperature which is about 45 degrees Celsius. It is above the room temperature, that is the temperature of the surroundings. Then stop heating the water by removing the heat source. Start the stopwatch and note the reading of the thermometer after a fixed interval of time. It is after every 1 minute of stirring gently with the stirrer. Continue to note down the temperature T2 of the water till it attains a temperature about 5 degrees Celsius above that of the surroundings. Suppose the temperature of the surrounding is 40 degrees Celsius, then you have to continue to note down the temperature in equal interval of time till it attains the temperature about 45 degrees Celsius. Plot a graph by taking each value of temperature difference delta T, which is T2 minus T1 along y-axis, and the corresponding value of time t along x-axis as shown in given figure. You will get a curved line. From the graph, you can infer how the cooling of hot water depends on the temperature difference from that of surroundings. You can notice that initially the rate of cooling is higher and decreases as the temperature of the body falls. This activity shows that a hot body loses heat energy to its surroundings in the form of heat radiation. The rate of loss of heat energy depends on the difference in temperature between the body and its surroundings. From the previous activity, you have seen that rate of cooling of the hot water is higher initially and it decreases when the temperature of the hot water falls. That is, it is the exponential function with respect to time t. How can it express mathematically? We have Newton's law of cooling, which is mathematically given as minus dq by dt is equal to k T2 minus T1, which is the expression 1, where k be the positive constant that depends on the area and nature of the surface of the body under the consideration. Consider a body of mass m and specific heat capacity S is at the temperature T2. Let T1 be the temperature of the surroundings. If the temperature falls by a small amount dT2 in the time interval dt, then amount of heat energy lost is dQ, which is equal to ms dT2, since specific heat capacity S is equal to dQ by m dT2. Therefore, rate of loss of heat energy is given by dQ by dt is equal to ms dt2 by dt, which is the expression 2. From the equations 1 and 2, we get minus dQ by dt is equal to k T2 minus T1, which is equal to minus ms dt2 by dt. So, ms dt2 by dt is equal to minus k T2 minus T1. Then dt2 by T2 minus T1 is equal to minus k by ms dt, which is equal to minus capital letter K dt, where capital letter K is equal to k by ms. Then dt2 by T2 minus T1 is equal to minus k dt, which is the expression 3. On integrating the expression 3, we get logarithm of T2 minus T1 is equal to minus kt plus c. If you take the expression in the form of exponent, you will get e the power of logarithm of T2 minus T1 is equal to e the power of minus kt plus c, which is equal to capital letter C into e the power of minus kt, where capital letter C is equal to e the power of c. Then T2 is equal to T1 plus c into e the power of minus kt, which is the expression 4. The expression 4 is used to calculate the time of cooling of a body through a particular range of temperature. Let us discuss on numerical. First question is, the triple points of neon and carbon dioxide are 24.57 Kelvin and 216.55 Kelvin respectively. Express these temperatures on Celsius and Fahrenheit scales. You mean triple point of a particular substance is a point such that there is only one temperature or pressure in which the three phases of the substance coexist in equilibrium. How can we relate Celsius scale and Fahrenheit scale each other? It is expressed as F minus 32 whole divided by 18 is equal to C by 10, or F is equal to 9 by 5 C plus 32, where F be the Fahrenheit scale of temperature and C be the Celsius scale temperature. In case of neon, the triple point is 24.57 Kelvin. When it converts into degrees Celsius, we have to subtract 273.15 from 24.57. It is equal to minus 248.58 degrees Celsius. Then we have F is equal to 9 by 5 C plus 32. By substituting the values, we get C is equal to 415.44 degree Fahrenheit. For carbon dioxide, the triple point is 216.55 Kelvin. When it converts into degrees Celsius, we get it is minus 56.60 degree Celsius. by using the same formula and by substituting the values, we get F is equal to minus 69.88 degree Fahrenheit. Let Ta be the triple point of water on scale A and Tb be the triple point of water on scale B. Since Ta is equal to Tb is equal to Tk, then 200 A is equal to 300 B. So, A is to B is equal to 350 is to 200. It is equal to 4 is to 7. Therefore, the ratio Ta is to Tb is equal to 4 is to 7. And third question is, a copper block of mass 2.5 kilogram is heated in a furnace to a temperature of 500 degrees Celsius and then placed on a large ice block. What is the maximum amount of ice that can melt? Given specific heat of copper is equal to 0.39 joule per gram per Kelvin and heat of fusion of water is equal to 335 joule per gram. Here, given that mass of the copper block M is equal to 2.5 kilogram, converting into gram, it is equal to 2500 gram. Rise in temperature of the copper block delta theta is equal to 500 degree Celsius. Specific heat capacity of copper SCU is equal to 0.39 joule per gram per Celsius and heat of fusion of water L is equal to 335 joule per gram. What should be the maximum heat the copper block can lose? It is expressed as Q is equal to M SCU delta theta. By substituting the values, we get Q is equal to 4,87,500 joules. Let Mn gram be the amount of ice that melts when the copper block is placed on the ice block. Then the heat energy gained by the melted ice Q is equal to Mn L. So, Mn is equal to Q by L. By substituting the values, we get the maximum amount of ice that can melt is equal to 1455.22 gram. Converting into kilogram, it is equal to 1.45 kilogram. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.